Hello again everybody and welcome to this video. Today we're going to look at probability of independent and dependent events. Okay, so let's look at what independent events are first. When the probability of one event occurring does not affect the probability of another event happening, that's independent events. An example of this would be to determine the probability of drawing a king, replacing the card, and drawing a second king from that standard deck of cards. So if we look at the probability of the first king, it would be, well, kings, there is I'll call that A. There are 4 kings out of our 52. Okay, we pull that card out, we put it back in. When I look at the probability of the second king, it would again be 4 out of 52 because there's still 52 cards in the deck. All 4 cards are in there. All right, so those are independent events. Dependent events. When the probability of one event occurring does affect the probability of another event happening. So in this example, let's determine the probability of drawing a king, not replacing the card, and drawing a second king from a standard deck of cards. So the first king would be 4 out of 52 because there's 52 cards. Now we're going to keep that card out. When I go to draw the second king, now there's only 3 kings in there and there's only 51 cards total. So you can see we have a different probability than what you're used to seeing. So these would be dependent events, that first king affected the second king. So summary of independent dependent. Regardless of the type of events occurring in independent or dependent, these problems are simply AND situations, meaning we must multiply the individual probabilities in order to determine the overall probability. So if I go back to the first one, I could have just simply multiplied 4 over 52 times 4 over 52. In the second one, it would have been 4 over 52 times 3 over 51. Now, there is a little formula, just like the OR situations and the AND situations, there's a formula. What they look like they're really the same thing, but for independent, we go the probability of A and B occurring would be the probability of A multiplied by the probability of B. For dependent, like I said, it's going to be something that's very similar. So the probability of A and B both occurring, it's the probability of A being multiplied by the probability of B given A has occurred. So that's what this means. Okay, it's the probability of B given A has happened. So that's where our 3 over 51 would come in, right? It's a little bit different. In this other one, it was still 4 out of 52 because we replaced the card, but in the dependent, we didn't replace the card, so that notation just kind of helps remind you of it. So really, we're just multiplying our probabilities. Whether you use those formulas or not, that is up to you. Okay, let's work on the first example. Alin rolls 2 4-sided dice and tosses 1 coin. Determine the probability that the product of the dice is an odd number and the coin lands tails. All right, we're working with 2 4-sided dice and we're tossing 1 coin. Just like in a previous video, I think whenever we're dealing with these dice and things and outcomes, it's nice to actually just look at a table. Now it says the product of the dice. All right, so I'm going to make a multiplication table this time. And again, sorry about that, just like last time, kind of kills some time here. And it said product of the dice, so that's why we're multiplying. All right, so those are all my possible outcomes. Now, like the other section 2, why don't we define, we're going to get very proper here, and we're going to say A represents an odd product. And the event B will represent the other, which is coin, oh, that's right, tails. We know what we're talking about. And now, this and here, that's the big key. It's telling us that we're in one of these and situations, so we're multiplying our probabilities. So, oh, geez, I'm having lots of trouble with my pen working, people. Sorry about that. Give me 1 second to see if I can make a little adjustment here. Sorry, guys. There we go. Now it's kind of working. So the probability of A and B would be the individual probabilities. So probability of A times the probability of, well, now it's either B or just the B given A's happen. So are these independent or dependent events? So are they related to each other? Will one affect the other? They won't. So these are going to be independent. So if it's independent, this will just be a B here. So I see some blue marks in my way here. Just give me a second, and I'm just going to see if I can erase those. Okay, I think I should be good now. So the probability of A, the odd product. Well, if I go over to my table over here, I'm going to look at all the odd products. So 1, 3, 3, 9. That's it. So it looks like there are 4 odd products, and then out of 16, there's 16 total outcomes. Being multiplied by B, what's the probability of a coin flipping and landing on tails? Well, hopefully you know that's 1 out of 2. And then I just multiply. So I like to reduce first. So I see 4 and 2, they have a common factor of 2. Or another way of looking at it, I can divide both those numbers by 2. So 2 divided by 2 is 1. 4 divided by 2 is 2. I can also reduce the 2 and the 16. They're both divisible by 2. So 2 divided by 2 is 1. 16 divided by 2 is 8. And I'd work that out to 1 over 8. You can do it the more basic method where you just multiply straight across. So it'd be 4 over 32 and then reduce from there. These numbers are small, so that would work. But anyway, there's our first example. Example 2. A jam manufacturer knows that in a box of 48 jars, 5 will contain less jam than shown on the label. Determine the probability that 2 jars drawn at random will contain less jam. So what we're looking for is we're going to draw a jar. It's got less jam, and another jar. It's got less jam. So again, this is an and situation. A will be first jar with less, and then B will represent the second jar with less. Okay, so here's my formula. Probability of A and B happening. I'm just going to multiply these things. But again, remember, once we get here, we have to decide, is this thing independent or dependent? So, will the probability of pulling my second jar, will that be affected by pulling my first jar? And it will actually. Now let's go over the logic as to why. The first jar, we know that 5 contain less jam. So I know that 5 jars out of 48 contain less jam. On that, once I've pulled it out, once I go to pull the second one out, now there's only 4 of those jars left. And there's only 47 jars total in this box. So when I go to multiply that now, I'd get 20 over 2,256. And I can actually reduce that to 5 over 564. Again, don't get too lost on the reducing. I want the actual math and the logic behind it. Now, one thing that might not jump out in this question is it doesn't really talk about putting one back, but it says that we're drawing 2 jars out. So you need to grab, like, you're going to have 2 out in the end is what that's trying to say. So, of course, then if you knew that, you'd pull out one and then you pull out another one. Okay? So, and again, I actually could maybe reword that question to say, you know, pulling out 2 jars one at a time or something like that. So sometimes these questions, the wording can be kind of gray. So make sure you talk to your teacher so you know exactly what you're being asked. Example 3. Marcel works 2 shifts a week at a coffee shop, one on a weekday and one on the weekend. He's available during the week from Tuesday to Thursday and on both days on the weekend. His boss randomly chooses which shifts Marcel will work. Determine the probability that Marcel will work on Tuesday and Saturday. Okay, so, oh, there's my pen going. So A is going to be We'll say what came first here? Weekday. So that's going to be a weekday shift. B is going to be a weekend shift. So now why am I doing this? Well, just to give some more meaning to my formula. So it's an and situation. It says here work on Tuesday and Saturday. So that's what we're looking at, the probability of, well, what am I saying here? That's exactly what this should say. I'm sorry, everybody. This would be my Tuesday shift. And this would be my Saturday shift. Sorry about that. I'm worrying so much about my pen working that I'm kind of forgetting some of my language here. Okay, so this is the probability that he'd work on Tuesday times the probability he'll work on Saturday. And then should I slap in that /A? Like, is this independent or dependent? And it says he randomly chooses. So really, it's not going to matter which day which day of the week he's working. It's not going to affect his weekend. So I'm going to say these are independent. So that would just be like that. So the probability of now working a Tuesday shift, well, there's one Tuesday out of the weekdays that he's available, and that's Tuesday, Wednesday, Thursday, so that'd be 1/3. And then on the weekend, Saturday is one of those days out of the two. So my probability would be 1 out of 6, 1/6. That's the probability that he will work on Tuesday and Saturday. Example 4, Tony draws a card from a well-shuffled standard deck of 52 playing cards. Then he draws another card from the deck without replacing the first. Determine the probability that both cards are jacks. So hopefully something that pops out to you guys is it says without replacing the first card. So without replacing, that's telling me right away that this thing's going to be dependent, so that the probability of the second card will be affected. Okay. You don't need to go through this A-B thing every single time. You do not need to. I'm just trying to present things in a nice, easy order. So this will be my first jack. And this will be my second jack. So the probability of A and B, the probability of the first getting a first jack and a second jack will be probability of A times the probability of B, given that A has occurred. So the probability of A. Well, how many jacks do I have? Well, I have 4 jacks in the deck out of my 52 cards. And then now I'm keeping that card out. How many jacks left over? There's now only 3 left over out of how many cards? 51, because again, I've kept that one card out. So again, I can multiply, but I see here I can divide these both by 3. So then I'm going to get 4 over... Well, before I even do 4 over, everybody, you might be already thinking, I can reduce these. This would be 1 over 13 as well. So then I'd actually get 1 over, that's going to be 221. So sorry about the messiness there, though. And again, I'm more worried that you can do this, like the 4 over 52 times 3 over 51, than the reducing of the fraction, because the fraction, as long as you multiply it correctly, it's the correct answer no matter if it's in a reduced form or not. I want to make sure you get this logic right. All right, example 5. 2 standard dice, 1 red and 1 green, are rolled. Harris scores a point if an odd number is rolled on the red dice, and a point if a multiple of 3 is rolled on the green die. It says in this first part here, and again, this will be A and this will be B, draw a tree diagram that shows all the possible outcomes. Okay, so we've gone over tree diagrams a little bit in class, but this is good to see this again. So we'll go through this. R is going to be the red dice, of course, and then G is going to be the green, everybody, so we know what we're doing here. So the probability for the red dice, and what's the red dice's criteria? It says an odd number is rolled. So how many odd numbers on a standard dice? So there's 6 sides, so there's going to be 3 odd numbers. Now you could also say that's 1/2. Let's see, this pen is going to work or not. So I'll say 1/2. Now, with a tree diagram, what you do is you kind of look at all the different situations. So now, R not happening. Now, let's maybe update this. Instead of red, I guess I can say This is going to be an odd number. And then instead of green, let's say multiple of 3. That'll make more sense here. So now, with R with a line over top, that means the probability of not rolling an odd, which would have to be an even then, so that'll be 1/2. And then what we do in a tree diagram again is now we go to the next phase of it. So now we're going to check out what happens on the green dice, okay, and then what the opposite would be. So probability of G, which is the multiple of 3. How many multiples of 3 on a standard dice? And here are the numbers. Whoa, I almost wrote a 6 there. You can see multiples of 3, there's 2 multiples of 3. So 2 out of 6, or 1/3. And then for now the next part, probability of not G, so not having a multiple of 3, that's all the other ones. So that'd be 4 out of 6, or 2/3, however you want to write that. Then this part, this is the exact same logic. So I'm going to have the exact same numbers here. There's not more math or new math to do. This is just part of the mapping. Like it's going to go through all the different scenarios. And I'll show you that now. So in B, it says determine the probability of Harris scoring 2 points. Well, for Harris to score 2 points, he has to get the red. Again, sorry guys. He has to have the red workout and the green workout. Okay, he has to get that odd number and he has to get that multiple of 3. So those would be the 2 fractions, and we know from talking about this now already. So I could write this out like this. And now, would this be dependent or independent? Does one dice affect the other dice? And it does not. What I get on the red won't affect what I get on the green. So it's going to be 1/2 times 1/3, so equals 1/6. The probability of Harris scoring 2 points is 1/6. C here says determine the probability of Harris scoring 1 point. Okay, well, to score 1 point, Harris is going to have to, well, there's 2 different ways. He can have the red dice work out, but the green not, and then have the red not work out and the green. So there's 2 different ways. It's an or situation. So let me write this out. So it's cases. I'm sorry, guys. This pen is really causing issues in this video. So we're going to get the odd, but not a multiple. Whenever I have just random squiggles in the middle of the screen, that's when you can kind of know that I'm having an issue with my pen, where I'm writing, it's not working, and it just randomly scribbles on the screen like that. So we have that tree diagram, but it's not in view right now. That's okay. You see that other squiggle pop up yet, people? Okay. I can only imagine how annoying that is. So that's where the red's going to work out and the green is not going to work out. Well, the red, that was the odd number. Remember, that's just going to be half again. And then now not getting a multiple of 3. Remember, multiples of 3 were 2 out of 6, or 1/3. And then we worked out that not getting multiple would be 2/3. So then I'd multiply that, and I can kind of do it older, the traditional way, 2/6 or 1/3. So that's one way of him scoring a point. The other way would be not getting an odd, but he would get the multiple of 3. So in notation, I would say not odd, but then getting the multiple of 3. So not odd, well, that's even, that's half the we have 1 out of 2 chances, or 3 out of 6. And then getting a 3, we said that there was 2 out of 6 chances, or 1/3. So then I would get 1/6 over here. And then this is cases, like I said, so we'd have to actually add this up. So I'd go 1/3 plus 1/6. Remember, when you're adding, you need common fractions or common denominators, so I'll change that. Oh, sorry, the 2/6 plus 1/6. So 3/6, which equals 1/2. So he's got a pretty high probability of scoring the 1 point. Okay, example 6. Mr. Troy, that's me, produces widgets. He knows, or I know, that when I make 130 widgets, that 7 will be defective. Sorry about that. Steve will select 2 widgets at random. What is the probability, in this first question here, of selecting 2 defective widgets? Okay, so A can be first defective, and B can be second defective. So the probability of pulling these 2 defective widgets would be the probability of the first one times the probability of the second, but is it independent or dependent? So if Steve removes his first widget and we know it's defective, and then now he goes to remove another one, that will affect things. So we're not putting these widgets back. So the first widget, we know that 7 are bad out of 130. And the second widget then, the second bad one, there's 6 bad ones left out of the 129 that are left over. Okay, and then we can get that answer. Okay, sorry about that. My pen wasn't working again. 861 over 16,770. Okay. That is not the right answer, obviously. That would be 42 over that. I'm sorry, guys, but 7 times 6 is obviously 42, and that's what you're thinking at home there, too, is like, what is going on? So it'd be 42 over that 16,770. And again, I'm not worried about you reducing that, so you can leave it like that. You could put it into percentage form, whatever. It's the correct answer in that form, though, as well. Okay, so for B, though, we're going to look at selecting exactly 1 defective widget. Okay, so this is going to be similar to the previous example where there's 2 ways for that to happen. The first widget could be defective, but then the second one won't be. That's one way to select one. The other way is that the first pick, it'll be a widget that works properly, and the second one would be defective. So we will look at that. Okay, so the first one here. That's going to be, I'm going to say defective and then not. So, and you don't need this, the formula all the time, so I'll show you in this one you don't need the formula. So defective, we know that the first one would be 7 times 130, because there's 7 defective. So now for not defective, I want you to think, well, how many widgets would not be defective if 7 are defective? Okay, well, 123, hopefully you thought of. If again, hopefully this pen will get going for me. So 123 out of, and I already removed 1 widget, so that would only be 129. Okay, and you can see, you'll see here now, this is 861. I got ahead of myself on my sheet, over 16,770. Then case 2, I'm going to say it's not, sorry, the first pick will not be defective, but the second one will be defective. So for not defective, we said there's 123. And I haven't picked anything out yet, so that's out of the 130 that are in the box. For defective, I haven't chosen a defective yet, so there are 7 defective in there, but there's only 129 widgets in that box right now. And you can see it's actually the exact same numbers, just in a different order, so I get the 861 over 16,770. And then the third thing we'll have to do is really add those cases. So if I add those together, I end up getting 1,722 over 16,770. So we'd add my numerators, leave that denominator alone.